Here's some more examples of improper integrals where the limits are improper. So we have this problem right here. First thing we do is graph it just to see what's going on. So here's all the area in here. Here's e to the square root of x, negative square root of x, diving down. And the question is, does all this area going to infinity, is it small enough? In other words, is the function diving to 0 quick enough for it to add up to a finite number, or is the function going down so slowly that all this area is eventually going to go to infinity? So that is the question. So we just investigate it numerically a little bit. Put the say a big number like 50. You know, our calculators, we don't want to run something more than 200 because it takes too long. So 0 to 50, and that gets you to 1.9899. That's pretty promising for it to converge to a number, but you still don't know. I mean, maybe it's creeping up so slowly that it'll just keep on going up. Anyway, that was Simpson 200. So let's just see what we have. Okay, basically two methods for the class. Method one is you already have the antiderivative given to you. So if we're on a test, you know, I could give you the antiderivative because I wouldn't want you to waste all the time finding that and then going through this improper integral business. So that'd be one way. Or it could be a problem where I want you to know how to get that antiderivative and do this. So those are the two methods, doing it all the way or doing it sort of halfway. So method one, halfway. You're given it, or you look up the indefinite integral, and here it is right here. Okay, so that's it. That's how to Wolfram alpha. So then you use our procedure, the integral from 0 to b, and b is going to be going to infinity. You put the antiderivative in there, you evaluate it out, you get here, and then you end up with this statement here. Okay, that's not too bad. Then we go up here and we realize that, okay, so our integral is equal to the limit as b goes to infinity. That's the definition of what this infinity means up there, which is equal to the limit as b goes to infinity of our expression that we figured out, which is this. Now, we are allowed to say that this denominator, e to the square root of b, that's an exponential function. That's blowing up big, fast. And that totally dominates over the square root of b plus 1. So that's going to 0. But if you didn't believe that, or if you wanted to prove that further, you could use, or if you were told to prove it further, you would use L'Hopital's rule, because it is the infinity over infinity case. As b goes to infinity, that's infinity, and that's infinity. So it is that case, so that's checked off. Take the derivative of the top and you get this right here. Take the derivative of the bottom and you get this by the chain rule. It just so happens that the numerator exactly cancels out with the denominator part here, and you just get 1 over e to the square root of b, and as b goes to infinity, that certainly goes to 0. Okay, so knowing that that goes to 0, this part right here, then that's just your 0 here. And so the whole thing goes to 2. And that did verify out with our Simpson up here, 1.9899. So apparently it does creep up, but it slams into a wall at 2 and limits out to 2. So that's all looking good so far. Method 2, you have to do it all the way from scratch and find the antiderivative yourself. This is a very peculiar type of problem, as it turns out, because you have used substitution, and then you're going to end up using parts. So this is what it's going to come down. Realizing this is a u substitution is unusual, because you're looking at that negative square root of x and you don't see a square root of x anywhere, you know, for the derivative to end up being inside a du or something. So it doesn't look like it's going to work out. Now, I use w because I know I'm going to be using a parts problem later. Of course, you wouldn't know that. You'd have to use U and then change the letter so you didn't get confused, or use a capital U later and a capital V. Anyway, so I used a W for the substitution, called it equal to this, and realizing that when you took the derivative, the W right here does show up in that's 1 over the W, so with the negative sign. So it is promising. So then I rewrote it this way with the square root of x in the denominator, realizing that here is my W. So I am going to get lucky because I get down to here, and then I multiply both sides by 2w and solve out this way with these differentials. So the dx is really 2w dw. Very unusual. Of course, that doesn't really solve the problem quite yet, because when we go down to here, we have subbing everything in. Let's leave that on it. dx is 2w dw, that's this, and you have the e to the w because that was what w was. So here's your dx, and here's your 2w dw. Okay, so everything's matching up. Factor out to 2, and now I'm here, and this is definitely a parts problem in its own. So now I got to start over with the parts on w e to w, and we've probably seen that integral before, but what you want to do is do this procedure, call that u, call that v, or dv, and you get v equals this, du equals dw. You know our procedure. Map out the parts, and you get the solution is right here, which then factor out, we'll go over to here, the original integral that we're trying to find out is equal to 2 times the integral of w e to w dw from above. So that turned out to be, the answer to that was this. I did this funny business of C1 because the 2 is going to multiply in on the C1 and give me C. I like to end up with C, so I call the previous one C1 when a constant is being multiplied by it. And then I put in what W was, which was the square root of x, negative square root of x. Factor it all out, and you get exactly what Wolfram Alpha said was the antiderivative in the first place. And then you would proceed, as we did above, from then on out to handle the improper limits and get the answer, which was 2.